In today's video, we look at matrices again. Specifically, we look at two new measures of a matrix, known as the rank of a matrix and the nullity of a matrix. So these two measures have to do with three vector spaces in particular. Two of them are new, known as the column space and the row space of a matrix. These have to do with what's known as the rank of the matrix. And the nullity of a matrix corresponds to a vector space that we already looked at, the null space of the matrix. Okay, so we let A be an M by N matrix. The subspace of Rm that is spanned by the n columns of A is called the column space of the matrix A. And its dimension is said to be the column rank of A. The subspace Rn spanned by the m transposed rows of A is called the row space of A. And its dimension is said to be the row rank of A. And so when we deal with any matrix, we get two vector spaces out of it. We get what's known as the column space and the row space. Right? So the dimension of this column space is the column rank, and the dimension of the row space is called the row rank of the matrix. All right, so let's look at this matrix given right here. We wish to find a basis for the column space of A and determine the column rank. Now, here's how we do it. Take the matrix. Right? Now keep note that each column is going to represent a vector in the column space. So we'll call column 1 U1, column 2 U2, right, U3, and U4. So there are four vectors within the column space. Since we're trying to find a basis for the column space, right, we're trying to find a set of linearly independent vectors that span the column space. Well, remember how we did that if we were given a set of vectors that already span the column space, which we have here. These vectors are going to span the column space. All we did was row reduce it to determine which vectors we eliminated to guarantee a set of linearly independent. Well, to do that, we just row reduce the matrix. And if we row reduce this matrix, this is what we'll get. Right, we look and we go, okay, so column 1 has a leading 1 in it, and so does column 3. So the vectors associated with columns 1 and 3 would form a linearly independent set of vectors that span our column space. Well, that would be U1 and U3. So a basis for our column space would be the set 1, 2, 3 and 0, 1, 1. And let's represent column space as col of A. Right, since there are two vectors in the basis, that means that the dimension of this column space is 2, which means the column rank itself is also equal to 2. If two matrices A and B are row equivalent, then the row space of A is the same as the row space of B. In other words, the row spaces of row equivalent matrices are the same. So first, let's note performing any row operation on a matrix A results in a matrix, let's call it A1, whose rows are simply linear combinations of the rows of A. Therefore, the row space of A1 would be a subset of the row space of A. Now that's just for performing a single row operation, right? If we repeat this reasoning for each subsequent row operation, until we get to the matrix B, then we'll find that the row space of B, which I'm just going to call row of B, is a subset of the row space of A. So we now have that the row space of B is a subset of the row space of A. What we want to do now is show that the row space of A must be a subset of the row space of B. Well, notice that we can perform row operations on B to get to A, right? So we can perform a series of row operations on B to get to A, right? Which obviously then implies that the row space of A would be a subset of the row space of B, right? So they're subsets of each other. We can therefore conclude that the row space of A must actually be identical to the row space of B. That's what it means if two sets are subsets of each other. Right, so the non-zero rows of a matrix in row echelon form that is row equivalent to a matrix A forms a basis for the row space of A. Now, this is going to be offered without proof. But if we wish, what this theorem is saying is if we wish to find a basis for the row space of A, we just take the matrix, row reduce it, and the non-zero rows forms our basis. So this is the same matrix as we had in example 2. All right, row reduce it gives us this. And we look at the non-zero rows. In this case, rows 1 and 2. Now, all I have to do is take their transpose, and those vectors form a basis. So we have the vectors 1, -1, 0, 1. And 0, 0, 1, negative 1. And these two vectors form a basis for the row space of A. Right now, that, of course, means that the row rank is equal to 2. Now, recall that in example 1, we found that the column rank was 2. And so is the row rank. So this leads to our next theorem, which simply states that the column rank and row rank of any matrix are the same. This will again be offered without proof, but that leads us into our definition of what we mean by the rank of a matrix. So the rank of a matrix A, denoted just simply as rank of A, is the row or column rank of A. Since they're equal, it doesn't matter which rank you find. So we now wish to find the rank of this matrix. Well, all that this means is we have to find the row rank or the column rank. So take the matrix. Row reduce it. So if we row reduce this matrix, this is what we get. Now remember, the row rank is the number of elements in a basis for the row space. And we found, that the non-zero rows of the row reduced matrix forms a basis. So really, all we want to do is look for the number of non-zero rows. Well, there are 3 of them, right? Non-zero rows in the RREF of A, which implies the row rank is 3, or simply the rank of A is equal to 3. Well, this leaves us with one more quantity of a matrix to define, and that's the nullity. We say the nullity of a matrix A, which is simply known as nullity of A, is the dimension of the null space of A. And recall what we said the null space of a matrix was. The null space of a matrix is simply the set of vectors that form a solution to the homogeneous equation AX equals 0, right? Well, let's find the rank and nullity of this matrix. All right, well, first for rank, we know how to start. Right, we start with our matrix and row reduce it. And we look for the number of non-zero rows. There's 1, 2, 3. So the rank of this matrix is equal to 3. Now, to find the nullity, let's first find a basis for the null space. And what we're still looking at this row-reduced form. Right? If we write that out, we get x1 is negative 2x3 minus 2x5. x2 we get as negative x3 minus 2x5. We find that x3 can be any free variable. Let's call it t, which is some real number. Then we'll see that x4 is simply x5. And then x5 can be any real number, so let's call that s. Let's write this out, right? So we get negative 2t minus 2r, negative t minus 2r, t, s, and then s. I'm sorry, let's call x5r. I don't know why I mixed everything up. So we'll call x5r instead of s. There we go. Well, let's break this down. We have a vector for just the t, so we have negative 2t, negative t, t, 0, 0. Plus then our r vector, negative 2r, 0, r, and r. We can factor out that t, be left with negative 2, negative 1, 1, 0, 0, plus, we can factor out that r, and we're left with negative 2, 0, 1, 1. Well, now what we've just found are two vectors that form a linear combination of our solution vector. So it obviously spans the null space. And also notice that these two are linearly independent. Right? So these two vectors form a basis for the null space. And I'm going to represent null space as simply null of A, which obviously means that the nullity of A is equal to 2. Right now, the rank was 3, nullity was 2, right? That's 5. Notice that that's the number of columns of A we have. Well, this is going to lead us into our next theorem. Our next theorem is called the Rank-Nullity theorem. And it says that if A is an M by N matrix, then the rank of A plus the nullity of A is equal to N. In other words, the rank of the matrix plus the nullity of the matrix is equal to the number of columns of the matrix. So, first, let's recall that vectors and bases for both column space of A and the row space of A correspond to the locations of the leading entries in the REF of A. Consequently, this means that the rank of A is equal to the number of columns with leading entries. In REF of A. Now, when identifying vectors to form a basis for the null space of A, we look for the columns in REF of A without leading entries. Right? That's because each of these corresponds to an arbitrary unknown right, which is a free variable, and thus a vector in a basis for the null space of A. Right? So what we find is that the nullity of A equals the number of columns without a leading entry. Well, since we have number of columns with a leading entry and number of columns without a leading entry, together they must form all of the columns in the REF of A, which means they form all the columns in A. So simply adding these two together, we get our desired result. We conclude by looking at now these following equivalent statements. Right? A is non-singular. A is row equivalent to IN. A is the product of elementary matrices. For every n vector B, the system AX equals B has a unique solution. The homogeneous system AX equals 0 has only trivial solution. The determinant of A is non-zero. The columns of A are linearly independent. The rows of A are linearly independent. The rank of A is equal to n. And the nullity of A is equal to 0. Right? So if any one of these 10 statements are true, then we know that the other 9 must also be true. In the next video, we are going to finish up our initial look at vector spaces by considering a change of basis. Right? So far we've looked at finding a basis for a vector space. We will now look at how, if we're given a basis, how can we change into another basis? Right? This will give us the idea of a coordinate, the coordinates of a vector within the vector space. So it allows us to write a vector in terms of a basis, and then how we can write that same vector in terms of a new basis. As always, I thank you so much for watching this video. I will see you all in the next one.